All right, so today I want to kind of continue discussing ways to try to embed or understand embeddings topologically and in the contact category in higher dimensions. And the technique I want to talk about today is what I'm calling braided embeddings. And just to kind of get us started, let me give you a sample theorem that we're going to try to prove by the end of the talk. But again, I kind of consider most of the talk as an advertisement for this idea of studying braided embeddings for contact and topological purposes. So, so what we want to try to prove here is the following theorem. So remember, yesterday we saw that there are obstructions to embedding a contact 3 manifold into the standard contact structure on S5, or actually any contact structure on S5. We saw in particular the churn class. The first churn class had to be 0. And the hope is that you could prove that a contact 3 manifold embeds in the standard contact structure on S3 if and only if the churn class vanishes. Well, unfortunately, we can't do that. But using these braided embeddings, we can kind of get some partial results. In particular, if your 3 manifold has no 2 torsion in the, well, the first homology or second cohomology, whichever you prefer, then you can actually embed it in the standard contact structure if and only if the churn class is 0. Sorry, an over-twisted structure if and only if the churn class is 0. Of course, that's a little bit restrictive, and we know over-twisted contact structures maybe aren't so representative of the sort of contact structures we're really interested in. So then we have the second result, or at least for simple 3 manifolds. So basically any lens space, S1 cross S2, S3, T3, so all your kind of simplest possible 3 manifolds you'd probably list when you're listing, starting to list 3 manifolds. We can pretty much embed those if and only if the churn class is 0. Although when you have a lens space with P even, we have a restriction here, unfortunately. We can't do it in complete generality. Just have a few partial results there. So by the end of the talk, we'll give a sketch of a proof of all of these results. But again, I'd like to spend most of the time talking about just braided embeddings in general. Oh, and I should mention, because we were talking about the isotopy problem earlier, you might be interested, these embeddings of all the, say, the contact structures on S3, what isotopy class are they in? We can actually get them all in the unknot isotopy class, so all like isotopic to the standard embedding. We can also actually find an infinite number of non-standard embeddings where we can embed everything as well. I'll talk a little bit more about that maybe in one of the later talks. But anyway, so this is our kind of theorem we're aiming for, and the main technique we're going to use is braided embedding. So let me just start out here by telling you what a braided embedding is. So we say an n-manifold M is braided about an n-manifold Y if there's an embedding of M into the product of Y and the 2 disk, such that when you kind of project just onto Y, you have a branched cover map. And I'm going to come back and give you talk about branched covers quite a bit, but just briefly, what's the definition that I'm going to use for branched cover? We say that basically M is a branched cover over Y. Well, P, a map from M to Y, is a branched cover if there's a codimension submanifold of Y such that in the complement of that submanifold, you have an honest covering map. Now, that's actually a little bit more restricted of a definition than you might normally hear. Normally, people just say there's some codimension 2 thing, that thing being maybe some complex, some CW complex, some PL something, whatever. I'm restricting to submanifolds because actually for the theorems I want to prove, I need it. You might be able to do something in more generality, but we haven't actually worked out the details of that yet. So for our purposes, whenever I say branched cover, I mean the slightly more restricted version of branched cover. Well, remember I said the branched cover has a codimension 2 subset where it's not a cover, right? Well, so if you're talking about 1 manifolds, say like S1, then of course codimension 2 is the empty set. So basically you're just talking about a covering map. So a branched cover is simply a map from, in 1 dimension, is simply a map from S1 to S1 cross D2, so that when you project onto the S1 factor, it's a covering map. That basically means that the embedding of S1 into S1 cross D2 is transverse to all the D2 factors. So that basically means it's a closed braid. So this definition of braiding 1 manifold about another is a clear generalization of the notion of a closed braid that, of course, has been very useful and effective in studying, well, in 3-dimensional topology, knot theory, the theory of 3 manifolds, mapping class groups. It's been a very, very rich subject, and I'd like to advertise that this more general definition you should think of as generalizing this, and might be as fruitful and productive in studying similar sorts of embeddings, isotopy, and other sorts of questions in high dimensions as well. Okay, great. So any questions about the definition of a braiding of 1 manifold about another? So this is kind of an abstract concept at the moment. It's not about braided embeddings quite yet. So now we'll move on to braided embeddings. So now suppose you have some larger manifold. Y is embedded in Y of a different dimension. OK, typo. The second Y is a W, as you can see from below. So suppose Y, our n-dimensional manifold, is embedded in W, a n plus 2-dimensional manifold, such that its neighborhood is just Y cross D2. So the normal bundle is trivial. Then we say an embedding of M into W can be braided about Y if you can isotope that embedding so that it maps into the neighborhood of Y, and sitting inside of the neighborhood of Y, it's just a braiding of M about Y. Okay? So you can braid a manifold about another manifold, and you can also try to braid an embedding about an embedding of some other manifold. Is that OK? All right. What? Yes, we'll actually get to that, but that's true. That's true, yes. So here's some questions you might ask about braiding embeddings, kind of the first thing when you see the definitions that you might ask. So the first one, of course, is, given M, can you braid it about Y? Is that possible? Well, I can actually tell you right now the answer to that question is definitely no in high dimensions, because it's actually known, I think I mentioned this maybe in the first talk, that there are, I think it's 7 manifolds, or it might be 9, 7, 8, 9, somewhere in there. Starting that dimension and above, there's actually manifolds that can't be realized as a branched cover over, well, sorry, if Y is the n-sphere, then there's actually n-manifolds that can't be realized as the branched cover over the n-sphere where the branch locus is an embedded submanifold. So, so in that sense, the answer is no, but again, you want to restrict your attention to the situation where the answer might be yes, and then see if you can do it. So I'll say a little bit about this in a moment. A slightly more refined question is, suppose you're already given a branched cover. I happen to already make Y the sphere, but that could still be a general Y. But given a general branched cover of M over Y, you can ask, can that branched cover be realized as part of a braided embedding? You would think that might be very easy. We're actually going to see that maybe it's not so easy. All right. Oh, by the way, just for the fun of it, for question 2, if you go back to the one-dimensional setting, right, if you have any cover of S1 over S1, right, that's just a simple n-fold cyclic cover, or actually it could be an n-fold cyclic cover and an m-fold cyclic cover, so disjoint unions. My covers don't have to be connected, by the way, in this case. Then it's very easy to actually see that there's infinitely many different embeddings, braidings about S1. That's very easy to do, right? That's just n braids, right? So, well, n plus m braids, I guess the way I said it, but. OK, so that's an interesting question. And then finally, I think the most interesting question about braided embeddings is, given any embedding of a manifold into a sphere, codimension 2, can you isotope it to be braided about the standard n-sphere in S n plus 2? By the way, I'm restricting to the codimension 2 case because that's by far, for my purposes, the most interesting. But you could ask these questions. You could go back and you could say, well, maybe that doesn't have to be D2. Why doesn't that be DK? And then you could talk about kind of a k-dimensional, codimension k braiding or something. That's also, I think, could provide interesting topological questions. But from the contact perspective, that's not going to be very interesting for us. So we're going to stick to the codimension 2. You could also say, why am I using the trivial bundle? Why don't I use a twisted bundle? You could do that, too. Actually, there's a whole lot of other things you can do that are very similar to this. This is part of a general question. You can think of a branched cover from M to Y as being some sort of like singular bundle, right? You can think of a covering map as kind of a bundle, like with discrete fiber, right? And then if you've got a branch locus, it's kind of a singular bundle. And you can think of, well, the product as being, well, it's a really nice bundle, but you could put some other singular bundle over here, like, I don't know, Lefschetz vibrations or other sorts of kind of crazy vibrations that might have singularities in them. And you could ask, when can you kind of find embeddings that respect the bundle structures? I think this is a very general question and very interesting that I think has been almost studied, well, it's been studied very, very, very little. And this is just one very specific example of it. Yeah? That's right. Along the branch locus, you'll actually have some kind of tangency. That's right. That's right. But away from the branch locus, it will be transverse to the disk. That's correct. Yes. Yes. And in fact, that's going to be very essential in a proof later on. Yeah. Good observation. Kind of the reason I'm looking at these. OK, good. So, so we have these questions. So let's see what we can do about some answers. So I'm actually going to start with question 2, surprisingly enough. So question 2. So some answers to question 2. So the first answer I want to give you, this is joint work with Ryo Furukawa, a graduate student. I think he just graduated from the University of Tokyo. Anyway, we proved that any cyclic branch cover, just as you had observed, any cyclic branch cover can be realized as a braid. Now you might have an interesting question. How many ways can you realize it as a braid? And it's kind of surprising because, like, for instance, take a two-fold cyclic cover. How many ways can you realize a two-fold cyclic cover of S1 over S1 as a braid? Well, infinitely many different ways. But what about, say, S3 over S3? I don't quite have a complete proof worked out, but I think there might only be 2. So I mean, it's an interesting, just studying the ways you can realize it are quite interesting. And of course, this has something to do with the isotopy classes of embeddings in general. Anyway, so we have this result. Scott Carter and Kamada had previously proven this, but only for two-fold covers and only in low dimensions. But they had a very explicit way of doing it where we have, well, I mean, here's the proof. It's actually very, very simple. You just, given your branch cover, your in-fold cyclic cover, you observe that there's a function h from y to c such that 0 is a regular value and the inverse image of 0 is your branch locus. And then you just look at this set inside of y cross c, and you easily see that this x, when you just project onto the y factor, that's an in-fold cyclic cover. By the way, I'm glad nobody asked me this question, but what do I mean by cyclic cover? I'll leave you to ponder on that throughout the talk, and you can maybe ask me about it afterwards. But you have to define cyclic cover right. It turns out if y has a lot of topology, you have to be kind of careful how you define cyclic cover. But if you do it correctly, then this all works out very nicely, and there's kind of a unique in-fold cyclic cover in the sense I want to talk about, and therefore x happens to be the same as m, and so you've embedded m as an in-fold. You braided m about y. Okay. All right, so the proof is quite simple. That you just have to construct this function h. Just for the sake of time, I won't do it, but it's actually a fairly easy exercise. I imagine almost everybody could probably do it with a little bit of thought. But it is important, by the way, for this that actually the knot be null homologous. I actually don't know how to do it if the knot's not null homologous. OK, great. So that's the first answer we have. The second answer we have is that there actually are branch covers that cannot be braided. That was actually a little surprising. I didn't quite expect that. But Carter and Kamada came up with the first examples. They gave one example, and they had some very complicated argument using fundamental groups about why you couldn't do something that I still must admit I don't understand, but I'm sure it's fine. Again, Ryo Furukawa and I managed to prove this result using contact structures, and we have infinite families of examples, and it's easy to construct many, many other infinite families of examples. And so we'll see how to do this by the end of the talk as well. But again, it's kind of interesting. This is a purely topological question, but the easiest way I know how to solve it is actually to use contact geometry. What? Oh, about the braiding thing here? Our example is, I think once you see the example, you're going to see that it would be quite simple actually to generalize it to higher dimensions. We haven't done it, so I guess I should say I'm not 100% sure it's so simple, but I mean, I would be shocked if there's any problems at all making it work in higher dimensions. Odd dimensions, of course. For the even setting, again, I would be shocked if it's not true, but I don't offhand know how I would do it, or how anybody would do it, but yeah. OK, good. So question 1, so remember question 1 was which manifolds M can be braided about which manifolds Y. Well, once you know that cyclic covers can be braided, can be part of a braiding, then it's very easy to show that any surface is braided about S2. Just because any surface, you have this hyperelliptic involution that realizes it as a two-fold cyclic cover over the sphere, and therefore you can braid it from the previous results. And then there's this really beautiful result from 1983. They didn't have the definition of a braided embedding. But as anybody that studied a lot of three-manifold topology knows, Hilden and Montesinos and also Lozano spent a lot of time studying branch covers. And they actually constructed a very explicit three-fold branch cover that they showed could be embedded in S3 cross D2 in exactly this braided way I've been talking about, even though they didn't give that general definition. And what they were really trying to do is they're trying to give a different proof of the Hirsch theorem that you can actually embed oriented three manifolds in S5, and they succeeded using branch covers in these braided embeddings. So again, this is maybe the first hint that maybe you might study general embedding problems by using these braiding ideas.
When you present this proving the previous theorem with hetero covers?
With what?
Threefold hetero covers cover all.
Yes. Actually, it's not true. In fact, these counterexamples are simple threefold covers, so they're dihedral covers as well. So you can't actually, there's tons and tons and tons of examples of threefold simple covers that do not embed, are not part of a braiding. So you have to really carefully choose. You start with some branch cover, and you keep manipulating it in a way until you can actually build that function h. But it's not immediate. You don't get it from just having the structure of a dihedral cover. Yeah, it's kind of interesting. So, okay, good. Other questions? All right, let's move on. So question 3. So remember, question 3 was, I think, the most interesting one. Basically, when can you braid one manifold, one embedding about, say, the standard sphere? And the very first result of this was back in 1923. So quite an old result. Alexander proved that basically, of course, any knot can be braided about the unknot. That's just the standard braiding procedure in S3. In 1990, so probably the first time the general notion of a braided embedded was only given in dimension 2, where Viro gave some lectures, I think it was in Osaka, where he proved that any oriented surface that's embedded in S4 can be isotoped so that it's braided about the standard S2. And then a few years later, Kamada really worked out the details. He actually gave a completely different proof than Viro had in mind. This is the only published proof out there about the braiding result. And actually, Kamada's given, I think, at least a couple of different proofs over the years. And then actually, very recently, a graduate student at Georgia Tech, Calais, has actually proven that a 3-manifold can be braided about S3, the standard S3. The one caveat there that's not true in these other two cases is that at the moment, the proof is only in the PL category. And we'll see below that you would much prefer to have this in the smooth category. So it'd be great if, over time, maybe this could be upgraded to the smooth category. But still, it's actually nice to know there's at least some braiding results in dimension of 3 manifolds in dimension 5. So you might ask, what happens as you kind of go up the dimensions? What about, say, a 4-manifold in S6, 5-manifold in S7, and so on? Well, it actually seems that if you study the structure of these proofs, they're going to start to fail very quickly once you kind of go up the dimensions very far. So you're probably going to need different ways of trying to study that problem if it's true at all, and it might not be true. I mean, who knows? Actually, I asked Viro about this, and he actually guessed that probably once you go up one more dimension or 2 at the most, it's probably going to start failing. And you can probably even find obstructions, but so far nobody's done that. Anyway, so that's what we know so far about braiding. All right. So I told you I was going to remind you a little bit about branch covers because this is a subject, it's a beautiful subject. I've come to really like it in the last few years, but it's not a subject that a lot of people are probably terribly familiar with. So I'd like to actually spend a little bit of time so that when we do our examples later on and try to prove our theorems, you'll be a little bit more familiar with what branch covers really are. So again, we're purely in the topological setting. Let me remind you about branch covers. So how do you understand branch covers over D2? You can actually do this over any surface, but D2 is easy because it's got less topology, right? So we're going to stick to that. So suppose I have a bunch of points in D2, and I want to look at branch, say a k-fold branch cover of D2 branched over those points. So the first thing to observe, right, as we, from the definition, is that our branch cover is simply an ordinary cover of D2 over the complement of the points. And you can very, very easily prove that once you have an ordinary cover in the complement of the points, you can actually then kind of put those points back in the cover and the base and get a branch cover. So really, there's no obstruction to creating the branch cover once you've got the ordinary cover of the complement. So really, we have to understand is the ordinary cover of the complement. Let's check here. 16. OK, yeah, we're good. So recall, if you're trying to study ordinary covers, there's this kind of monodromy presentation of covering spaces. So again, this is something that might not be familiar to a lot of people. But of course, if you have, say, a k-fold covering, pick a base point downstairs. Above it, there's k points. Now, for every loop downstairs, right, there's the lifting, the path lifting. So lift it to a loop upstairs. And now that starts at one of the points. Well, it will end at one of the other points. So it kind of gives, for every path downstairs, you get a permutation of the points lying above the base point. that permutation is an element of the symmetric group, at least once you've labeled the points upstairs, right? So basically you wind up getting, and you can show that element of the symmetric group is independent of the homotopy class of the path, and therefore you get this group map from the fundamental group of the complement to the symmetric group. And this completely determines the cover. So I said given the cover, you get this map. It's also very easy, given this map, you can actually build then the subgroup that corresponds to the covering that you're interested in. So anyway, it's a fun exercise if you've never been through it. So, but yeah, I'm just reminding you of it here. So M determines the cover, but of course the complement of these points is simply a free group on N generators, one generator for each point that you removed. Therefore, this map, a map from a free group to some other group, is completely determined, or a homomorphism is completely determined by where the generators go. And you can send them anywhere you want because there's no relations that you have to satisfy. So basically, to understand this covering, all I have to do is, for each point, I just have to give you an element of the symmetric group. Okay? So this is an abstract discussion. How does this play out in reality? If you really want to build these covers, I claim you have these labelings, you can build covers. So let's do it. So here's a very, very simple example. So suppose you have the disk with 2 branch points, and I'm going to take a twofold cover, so I'm labeling with elements of the symmetric group S2. And of course, there's only one really interesting element. I don't know, actually the identity is pretty interesting too. But anyway, one non-trivial element. So we label both points with that non-trivial element. And now what are you supposed to do? Well, to build the cover, the easiest way I know to do it is you kind of take what I like to think of these branched cuts. So you cut each of those paths that generate the fundamental group, and you cut the disk along there, and you get this. And I'm going to straighten it out so I can draw the pictures a little bit nicer. And now if I want to take a twofold cover, every point in the disk has to have 2 points above it, at least except the branch points. So I take 2 copies. And I want to glue them together in a way so that I get a cover of the complement of the branch points. Well, when I go around this point, the 1, 2 means sheets 1 and 2 are supposed to be connected. So I basically have to glue sheet 1 to sheet 2 as I go around the point A. But to do that, I have to glue this little bit to this little bit. But you have to be careful, right? You have to preserve. You've got kind of a plus and minus side here. You have to glue things together so that you have kind of a well-defined map on the resulting space. So I actually have to put this little twist in when I glue. I have to kind of twist the upper one when I glue it down, or the lower one when I glue it to the upper one. And so for both points, since I'm gluing sheet 1 to sheet 2, I do it for both of those points. And I wind up getting an annulus here that's a twofold branch cover over the disk, which is something everybody already knew anyway, using the hyperelliptic involution, if you like. But this is a way to actually build it from the monodromy description of the covering. Is everybody OK with that example? OK. In that case, let's try a different example. So suppose you want to take the threefold cover of the disk branched over those 4 points, and I've given the 2 of the points, I'm just giving the 1, 2, so I'm going to connect sheets 1 and 2 and leave 3 alone. And for the other 2 points, I'm going to connect sheets 2 and 3, but leave sheet 1 alone. And so when you build it, I won't go through all the steps, but I take the 3 sheets, and when I go around points 1 and 2, I connect sheets 1 and 2, and leave the third sheet alone. I just kind of glue back up the cut. And then when I go around points 3 and 4, I connect sheets 2 and 3 and leave sheet 1 alone. And so you see I wind up getting a pair of pants is a threefold cover over D3 with branch locus 4 points. Okay? And so you can see now, if I give you any sprinkling of points in the disk and I give you any labeling at all, you can build the cover. And by the way, though, when I give you the labelings of the points, when I build that cover, it actually might not be connected, that sort of thing. So I mean, you have to be, if you want connected coverage, you have to be a little bit careful, but it's actually very easy from the data here to tell whether the cover is connected, to figure out the number of boundary components, and so on and so forth. OK, great. Let's move on then. So we've done the 2-dimensional setting. What about the 3-dimensional setting? Well, in 3 dimensions, you're branching over a link downstairs. Well, if you've got a link in S3, remember, the branch cover is going to be determined by a covering of the complement of the link. The fundamental group of the complement of the link is generated by meridians to each of the strands, say, in a diagram for the link. So basically, again, I just have to label each of the strands in a diagram for the link with an element of the symmetric group so that at crossings, the relations that show up in the fundamental group of the not complement are respected by the labelings. Well, that's actually kind of hard to explicitly build those covers. I don't know if anybody's ever tried to do this. It's actually kind of hard to even imagine what's going on there. But there's a nice trick you can do. So whenever I try to understand branch covers in dimension 3, I do the following. So you take your branch locus and you braid it. You braid it about the unknot. So basically, the way I'd like to say that is I isotope the branch locus so it sits in, say, this solid torus here, and it's transverse to the pages, to the disks. So I think of this as being like the pages, the vibration part of an open book, and this being a neighborhood of the binding of an open book. So I've kind of braided my branch locus about the pages of an open book. And now notice when I take the branch cover, I get an ordinary cover of V2. Well, an ordinary cover of V2 is simply, well, I unwrap it a few times and maybe take a few copies of that, right? So very simple. And what happens on V1? That's the more interesting thing. Well, notice when you're taking a branch cover of V1, each page is intersected some number of times. You have a bunch of points on the page. I'm just taking a branch cover of the disk now, right? So you're just taking a branch cover of the disk, and you get some surface there, and you get an S1 family of those. So you're going to wind up getting a surface bundle. Actually, I guess on the next page. You wind up getting a surface bundle over the circle that branch covers the solid torus. And we knew how to actually form the branch covers for each of the disks. And now all you have to understand is what's the monodromy of this thing, which is usually quite easy to work out. And here's a simple example where we do that. If you just take, for instance, this braid, when you take the two-fold cover, remember we already worked out that when you take the two-fold cover of the disk where you've labeled the 2 points by 1, 2, you get an annulus. And then it's a very, very easy exercise to see that, since there's this little half twist in the 2 strands, you wind up getting kind of a full twist around the core of that annulus. So you wind up actually getting an open book decomposition for the upstairs manifold where the monodromy is a full Dane twist. And it's an easy exercise to see that's simply S3. So basically, this is a well-known fact if you've never worked it out before, but the two-fold cyclic branch cover over the unknot in S3 is S3. Okay. Great. That's one that's easy to work out on your own, but this is just an example of using the strategy to see how to do it in general. So let's look at a more interesting example that you probably couldn't work out if you didn't have this little trick to do. So if I gave you this knot, as I said, each strand I'm going to label with an element of the symmetric group, 1, 2, 1, 3, or 2, 3. So I'm going to get a 3-fold cover. And I'd like to know, what do I get here? Well, remember we already said if you had a disk that has 4 branch points. So just look at the transverse disk right here. It's got 4 branch points, and they're labeled. They're labeled. 2 of them are labeled 1, 2, and the other 2 are labeled 2, 3. We know the branch cover of that is the pair of pants. We already worked that out, right? Well, what is the monodromy upstairs? Well, what happened downstairs? I put a full twist in all the strands. So kind of you can think of, if you take the disk and you put the 4 points in the disk, what I've done is I did a Dane twist around the boundary of the disk. So it kind of just twisted all the points. Well, that Dane twist, basically since when I take the branch cover of the disk, branch over those 4 points, I get 3 boundary components. The Dane twist lists to 3 Dane twists upstairs. And you basically see that that's precisely the open book you get for something. And I leave it as an exercise to you, although we might prove it later if we have time, that that's just L31, the lin space L31. Okay. So again, you can very explicitly work out tons and tons of examples by this nice braiding kind of trick. So this is the way I think it's easiest for me, at least, to understand branch covers in dimension 3. OK. So remember, our talk's here about contact geometry. So let's, we've spent the last 30 minutes saying almost nothing about contact geometry. So let's bring that back into the picture. So how do branch covers and contact geometry relate? Well, if I have my branch cover here with branch locus B, and you have a contact structure on Y such that B is a contact submanifold. So we already kind of have to know if you have a contact submanifold to even get started here. But let's assume that you have this contact submanifold. Then it's actually really very easy to see that contact structures pull back to covering spaces. So in the complement of my branch locus, the contact structure C pulls back to give me some contact structure in the cover. And it's a very easy exercise to see that you can actually extend that contact structure or slightly perturb it and then extend it over the branch locus. And moreover, there's actually a unique way to do that. And I'm going to denote the resulting contact structure C sub B. The construction first appeared in Gygas, although I think the details first appeared in Gygas. Did I say details? I didn't. I should have said. But I think certainly in earlier it was in Gromov's book, and it's essentially everybody knew about the construction. But the first time I saw an explicit proof written down carefully was in Gygas's paper here. And then many years later, the uniqueness part was proven here. But again, this is also folk knowledge. I mean, lots of people who have thought about this already knew the result. But again, it's nice to have good proofs written down. And the first proof appeared there. So great. So given a branch covering map and a contact structure on the base that's such that the branch locus is a contact submanifold, you get a uniquely defined contact structure in the covering space. Okay. All right, great. Rio and I were kind of studying this problem. By the way, notice this contact structure C sub B, it doesn't depend just on the branch locus. It depends on the realization of it as a contact submanifold. So if you take a different realization of this as a contact submanifold, you might get a different contact structure. And in fact, here's a nice simple example of that. Remember, in dimension 3, a contact embedding is simply a transverse knot. So suppose I have a branch cover of 1,3 manifold over another, and we have a contact structure C on Y downstairs. Take two different transverse realizations of the branch locus, where one of them is a stabilization of the other one. I don't think I've defined stabilization, but it's basically a way to take a transverse knot and get a new one. I'll say a lot more about that in a subsequent talk, but it's basically a way to generate new transverse knots from ones you already have. So if you do that, you can actually very easily work out that more typos. So the contact structure here, that should be a prime. The contact structure for the stabilized one is simply the contact structure for the non-stable you get from the non-stabilized one, connected some with S3 with this. Remember, I told you that there's an integer's worth of overtwisted contact structures that were distinguished by their D3 invariant, and this was one of them, the one that had D3 invariant 1. So basically, this is precisely what you get, and the proof is actually very simple. The idea is that if you have a transverse knot, you get the stabilized knot simply by, in a neighborhood of a point, so in some little ball, you simply kind of do some little perturbation, but leave it exactly the same everywhere else. So when I take the branch cover, oh, by the way, I guess I didn't define simple. By simple, the definition of a simple branch cover is one such that above every point in the branch locus, you're going to have, if you've got a k-fold cover, you're going to have k-1 points. What that means is, for k-2 of those points, it's not really a covering, it's not really a branching there. It's kind of an honest cover there. And at one point, you basically have an order 2 branching. And it turns out in dimension 3 that given any covering map, you can perturb it a little bit and make it one of these simple branch covers. Anyway, so given the simple branch cover, then all of this is true. And again, the proof is you have the stabilization is just altering things in a little ball. And now, so when I look at the branch cover of these two things, they're going to be exactly the same away from this little ball. And in this little ball, the inverse image of this little ball is going to be k-1 balls upstairs, because the branch cover of a ball over an arc is a ball. So I've got k-1 balls. K-2 of them are just going to be standard balls, because there's no branching. So it's just like a Darboux ball. You've done nothing. But one of them, the difference here, one of them will be, one of them is going to be standard for the kth one, where the other one is actually just an explicit computation. It will be over-twisted, and you can compute what the invariants are, and you just compute that it's exactly what I said it was. It's the one with D3 invariant -1. Okay? You okay with that? All right, good. Anyway, this will actually be very useful for us later on, but it's just nice to kind of see the way that the realization of the branch locus as a contact submanifold kind of comes into play. Okay, good. So that's branch covers. But we're not interested in branch covers, we're interested in braidings, right? So let's bring braidings into the picture. So here's the main technical theorem that kind of makes all of our results work.
So the high-D version would be, if you have an S5 and you decide an S3, and you branch cover along the S3, and you get a little thing, and then you can define these things.
Sure, yes. But of course, when you have those, an analogous theorem is not clear, right? Because you're not exactly sure what you're going to mean by stabilization. There are certain things you can do, but I'm not exact.
The next one would be S3. With that S3.
With what S3?
Did you never just S3 instead of the S5?
Well, but you might ask these questions. Suppose you're only embedding the standard S3 into S5. I think there's still going to be some notion of stabilization that might lead to something similar, but I'm not sure. I know we can talk more about it. The higher dimensional setting, I'm really not sure what the analogs of this are, but certainly the branch covering, you certainly can do all of this and ask questions, similar questions, and so on. But okay, great. So here's our main technical theorem. So suppose we have a braided embedding, a braiding of M about Y. Okay, so here's the data for that. And I need this extra condition that P is not multiply ramified. What does not multiply ramified mean? It means that if you take a point in the branch locus and you look above it, there's going to be a bunch of points. Only one of those points upstairs can have actual branching at it. The rest of them have to be ordinary points, really covered points. So in particular, simple branch covers are examples of not multiply ramified things. Cyclic branch covers are examples of not multiply ramified things. So there's lots of things satisfy this hypothesis. Okay, so that's our setup. The claim is given this, there is an orientation on the branch locus such that anytime you realize the branch locus in some contact structure on Y is a contact submanifold. So that's a big if. You have to be able to do that. But if you've done that, then this branch cover contact structure that is induced on M embeds in this specific contact structure on Y cross D2. Okay? So it's a bit of a technical result, but this is what we need. Oh, and by the way, the embedding is isotopic to the original embedding. In fact, all you've done is the embedding, you just start with the embedding E, and you start to crush M down toward Y cross a point. You yeah, anyway. And the proof, well, I say the proof is very easy, but of course I left out all the details. I claim basically if you just look at this, your embedding is just some map P, F into Y, D. And if you look at E sub R, you scale the F factor. I claim that if you just pull back this contact form by this, you get precisely the branch cover thing. So that's the claim, but when you actually work out the details, you start taking, alpha wedge, d alpha, blah, 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 that you have to do. You actually see there's some difficulties along the branch locus, and that's why there's this carefully worded thing about orientations to make sure everything works out right. And that's also where we need the not multiply ramified. If you've got different ramifications, if you've got different, above one point in the branch locus, if you've got different ramifications, actually this theorem might fail. I actually don't have an example where it does, but certainly the proof fails. So. Okay, good. So again, we're just going to use this result to try to prove all the stuff I mentioned to you at the beginning of the talk. So let's get started. So first of all, notice that if you take the standard S3 in S5, then that's an embedding of the standard contact structure on S3 into the standard contact structure on S5. That's easy, right? Great. Well, a neighborhood of S3 and S5, there's a regular neighborhood theorem that basically says it's just S3 cross D2 with this contact structure, which looks suspiciously like the one in our theorem, right? Not suspiciously, by plan, of course. Great. So notice if you have any three manifold that braids that can be braided about S3 and S5, then the branch locus for the corresponding branch cover of M over S3 can certainly be made transverse to the standard contact structure. Because remember we said earlier that given any knot, there's a C0 isotopy to make it a transverse knot. So you can certainly do that, and that means there will be some contact structure then on M that embeds in the standard contact structure on S3. So this actually says every three manifold has at least one contact structure that contact embeds in the standard S3. Okay? Great. So again, this is one of the reasons why I actually started asking these questions in the first place. I was very interested in, given an embedding of a three manifold, say into S5, can you isotope it so that it's transverse to the contact structures and induces a contact structure on the submanifold? In other words, you have a contact embedding. And the only way I could actually figure out to try to prove this is actually by observing the main technical theorem and then saying, well, if you can prove braiding, then you prove the result. And this is one of the reasons why it'd be great if you could upgrade the PL version of braiding to a smooth version, because that would then imply that every three manifold can be isotoped to be, every embedding of a three manifold in S3 can be isotoped to be a contact embedding. Okay? All right, great. So let's prove some of these results. So all contact structures on S3 can be contact embedded in the standard S5, smoothly isotopic to the standard embedding. So just to recall, the list of contact structures on S3 is simply the standard tight one, and then this one parameter family, this integer's worth of over-twisted ones. So I have to embed every one of those. Well, the standard one's obvious, right? Because just the standard way S3 sits in S5, that's a contact embedding of the standard contact structure. Well, there's a twofold cover of S3 over S3. We already talked about it, right? Branching over the unknot, the twofold cyclic cover. And that's a braiding. And I claim you can actually find this extra function to make it a braiding so that the resulting embedding in S5, what do I mean by resulting embedding? Remember, so S3 is braided over S3 this S3 we're thinking of sitting in S5 in a standard way. That gives a different embedding of S3 into S5, right? I claim that's actually isotopic to the original embedding. I mean, you have to check it, right? It's something you can check. It's just an explicit computation. We have an explicit formula for the F, and you just check. I say just check, actually. That's probably the thing that took me the longest to write down in the paper was actually checking that. But anyway, you just check. OK, well, great. So we got this set up. Well, now, remember, in the standard contact structure on S3, it's actually known that there is a transverse knot, Tn, such that for all positive n, such that T1 has self-linking -1. Remember, we talked about self-linking in the previous, well, one or two talks ago. And then Tn plus 1 is just a stabilization of Tn. From our previous results, you can easily see, well, actually, this is something you have to check, but it's very easy that when you branch over T1, you actually just get the standard contact structure. But from our previous results now, when you branch over Tn, you get the result of branching over Tn minus 1 and connect some C1. So you actually wind up embedding all the overtwisted structures with D3 invariant positive. Okay? So we've got half of the overtwisted contact structures embedded. What about the other half? Well, the other half have to have a little trick here. Realize in C1, which we've already embedded, right? We've already embedded C1. So we can now try to embed, we can now try to have a braided embedding of S3 about the S3 that has this contact structure induced on it. And inside of here, you actually have a sequence of transverse knots indexed by the integers such that 1 is the stabilization of the next one. So in other words, you kind of, anyway, it kind of goes infinitely. You've got self-linking numbers that are kind of infinite in both directions. And now, from the result above, we actually know that the branch covers of over these knots T prime n in C1, they're related by this. So you know the first one has to be some overtwisted structure. That's actually easy to prove. And therefore, the other ones, you get all overtwisted structures somehow in this family. So this gives you embeddeds of all overtwisted structures in the family. OK? Great. Well, from this, actually, we can actually prove a nice result that we actually stated earlier. Suppose you have a 3-manifold that has no 2 torsion in its second cohomology. Then it's actually known that there's exactly an integer's worth of homotopy classes of plane field with C1 equal to 0, and they're distinguished by their D3 invariant. The Hilden-Montesinos theorem tells us that there is some embedding of M3 into S5 braided about S3, and therefore you have some contact structure embedded. And therefore, by doing kind of ambient connect sums with the S3s, I wind up realizing all D3 invariants for contact structures on overtwisted contact structures on M. So this is embedded all the overtwisted contact structures with C1 equals 0 by this ambient kind of connect sum idea. And remember, I told you earlier we're going to prove that if there's no 2 torsion here, that we can embed a contact structure on M into the standard contact structure if and only if C1 is equal to 0. And this is how you do it. OK. Let's see. We've got about 5 minutes left. So let's move along. How do you prove that certain branch covers can't be part of a braiding? Okay. So, well, notice I've been picking my examples carefully because I actually want to look at the contact structure on L31 that comes from Legendrian surgery on this unknot. The claim is this has C1 not equal to 0, and therefore we know it does not embed in S5, right? It does not embed in S5 with any contact structure on S5. OK, well, notice this contact structure, I can actually realize it as a branch cover over S3, and you do it as follows. Well, you can actually fairly easily work out that an open book decomposition for this contact structure is given by this. Okay. Let's see, how's our time? Yeah, 4 minutes. Yeah, maybe I won't actually argue for that, but if anybody wants to see the argument, it's actually very easy to see that this is an open book for that contact structure. Well, remember, this open book comes from the branch cover over S3 over this link, right? Well, but this is a link. And remember, in our main technical theorem, there was orientations that were forced on us from the construction. And since this is a link, each of these components might have different orientations, and this is going to kind of screw up my trying to realize it as a transverse knot in a way where I really understand what's going on here. So I'd like to turn this link into a knot, and in particular, I'd like to turn it into a knot where orientation doesn't matter, right? Well, luckily, there's a really simple observation that if you have a simple branch cover, and you have two strands that are labeled with, say, ij and jk, you can put this kind of 3 twists in it, and you can get another branch cover that's exactly the same. Topologically, this is very easy because you can see the branch cover over this thing, over the ball containing this, is simply a ball upstairs. And similarly here. So that says you haven't changed anything. Well, you can also check that the branch cover of this thing over the ball is a tight ball upstairs. And the branch cover of this is also a tight ball, and there's a unique tight contact structure on the ball. So that basically says in the contact world, you also haven't changed anything by doing this change. Well, that says I can take my link and I can add 3 twists in the middle strands and then 3 twists in the top 2 strands. And this gives me a knot whose branch cover is still this contact structure I'm interested in. And you can easily check this knot. If I reverse the orientation, I get the same knot up to orientation. So it doesn't matter what our technical theorem says the orientation has to be. I get it, right? And therefore, if you could realize this branch cover as a braiding, then you would have embedded this contact structure in S5, which you can't do. So there's no way you can choose kind of this auxiliary function from the lens space to H so that P comma that function is a braided embedding. Okay? And you can easily see all you have to do to construct other examples is just find examples of contact 3 manifolds whose C1 is not 0, write down open books, see how to realize those as branch covers, make sure that I can then make them a knot that's where orientation doesn't matter, and I've got infinite families, many infinite families of examples of things that don't embed in the standard, that can't be part of a braiding. Okay? All right. Okay, how do I embed all the contact structures on lens spaces? I guess given that we have 2 minutes, this will go a little bit fast. Well, if you have a lens space, you can, it's kind of a fun little exercise to show. We've actually got a classification of all contact structures on lens spaces. And you can actually prove that every contact structure on a lens space with Chern class 0, so the only ones that can possibly embed, tight ones that can possibly embed, come from Legendrian surgery on something that looks like this. And by looks like this, I mean you basically got this kind of symmetric unknot or kind of push-offs of it. Okay. So that's a fun little exercise. Well, then you sit down and spend days and days and days drawing pictures, and you realize that all of these knots, all of the Legendrian surgeries on these knots can be realized. Well, the open book decomposition that realizes them is basically this thing. So it's a planar surface. You do Dane twist, positive Dane twist about all the red, and depending on your lens space, you do some Dane twist on some of the green. And by the way, this is just an example, right? You might have more and more punctures in your planar surface there. But it's hopefully the picture is clear what it would be as you kind of increase this. Okay, well, so this thing realizes your contact structure with C1 equals 0, your tight contact structure with C1 equal to 0. Well, I can't do anything with that. So I claim you can stabilize this open book to get that. And again, it's fairly easy to do, but given that we have 0 minutes, I won't do it. But you can stare at this and you can easily get to that. And well, that picture, if you try to make it symmetric, you get this. And you can actually realize this surface is a 2-fold branch cover over this surface, branched over those 2 points, P1 and P2. Hopefully that's pretty easy, right? You just draw the line through here and take the 180-degree involution. Well, it turns out that the Dane twist about these red curves gives you S3, and then half twists about various green curves. I've only drawn one sample curve here, but various curves that run through the holes kind of as are indicated here will give you a braid in this open book whose branch cover will give you this thing. And that's how we, so we have this 2-fold cyclic cover over some link downstairs that gives us the contact structure upstairs. And 2-fold cyclic covers we can always realize as braidings, and therefore we can embed these. Okay. That went a little bit fast. If anybody's interested in the details, I'll be happy to kind of say more about this later, but we should probably try to wrap up. So let me just finish with some questions about braided embeddings. So braided embeddings give you very explicit ways of representing. I mean, an abstract embedding, like say you take Whitney's embedding theorem, you get some embedding of your manifold, or you use Hirsch, you have some embedding of your 3-manifold into S5, or higher dimensional analogs. But it's kind of hard to understand those. But if you can actually braid it, then you have this monodromy data and other data that kind of tells you what the embedding is. And you might hope to use that data to do all sorts of stuff, like maybe study the isotopy classes of embeddings, like you do for braid theory in dimension 3, and you do for braid theory in dimension 4, actually. That's been studied quite a bit as well. You could try to study regular homotopy classes of embeddings. You could try to understand, you could try to build ciphered surfaces. In particular, right, in dimension 3, if you have a braid representation for a knot, you can build an explicit ciphered surface. Well, can you do that in higher dimensions? Well, actually, at least in some cases, Ryo Furukawa has actually done that. But I think it's only in the case maybe for cyclic braidings. But it would be interesting to kind of do that in general. And then can you use the braided data to compute invariance? Again, in dimension 3 you can, but what about higher dimensions? Can you compute the Alexander invariance, like the Alexander polynomials, Alexander modules? Can you compute not contact homology, which I'll say more about in the last talk? And there's just tons of other invariants you could be interested in. And can you understand those directly in terms of the braiding data for the embedding? And that's kind of my hope. And again, these are very interesting questions, I think, even independent of contact geometry, just in the purely smooth world. So I think that's a great place to end. So thank you.
Any questions for John? So you developed through one?
Yep.
You cannot be braided inside S3 times D2.
Yes.
Would you say S3 times S2, would you get better?
You know, I don't know. I don't know. The questions are not identically the same, but they're very, very, very similar. In fact, Hilden and Montesinos have other papers about embedding into kind of products with S2s using branch covers. And those results were a little bit easier than they were for the actual embedding into, you know, S3 cross D2. So it is a different question, but I don't know the answer. I don't know if, in particular, this one could be or couldn't be. Yeah, I don't know. It's a good question. Yeah.
You said for one of these, you had this result, or one of your students have this result that I think it's true in the PL category, but not in the smooth.
It's known to be true in the PL category. It's not known whether it's true in the smooth category or not. Right.
Is there a reason why it's harder to show in the smooth category?
PL gives you a lot of structure, right? You can represent things combinatorially, and you can represent isotopies combinatorially, and that's a simpler thing to do. In the smooth world, right, you have just, yeah, it's you have a little bit more structure there to work with. But you know, again, I think it's likely to be true in the smooth world as well. But you know, yeah, I hope it's true in the smooth world. Yeah. Yes. And we did for the lens spaces as well, and the T3 and so on. I didn't do T3, but T3 is actually one of the easiest ones to do. But I don't think so. I don't think so. I don't see that would really help you. Interesting to ponder that a little bit, but I mean, off the top of my head, I would say it probably wouldn't help you at all. But I'd love to be proven wrong on that. But as far as I can tell, I don't see how that would really help you. Yeah.
Okay, thanks, John, again.
Thank you.